Right now, there's an object in our solar system that the textbooks don't know where to file. It's called Interstellar Visitor 3I, Atlas. And here's the problem. Hubble has just reinforced that it was never truly a comet. Not in the way we assumed. The jets look too balanced. The chemistry feels too off-key. And the way it keeps lining up with the sun, it defies probability in the quiet. Unnerving way that makes statisticians go still. For months, NASA labeled it an interstellar comet, but the numbers keep refusing to cooperate with that story. So, if it isn't a comet, what have we actually been watching drift through our cosmic neighborhood? Stay until the end, because what the math is hinting at may make you question everything you thought you knew about travelers between stars. And believe me, the implications are uncomfortable. If this mystery keeps pulling at your attention the way it pulls at mine, subscribe, so you'll hear the moment the next observation drops, and comment below where you're listening from, what time it is there, and whether the conservative explanation still holds, or whether we're staring at something genuinely unprecedented. Part 1. The announcement that shook the field. Picture this. A quiet Tuesday morning in July. 2:00 Arshawu. You're scrolling, half awake, mid-sip of coffee, and then you see it. A headline so strange it makes your hand pause in mid-air. Hubble confirms, mystery object may not be what we thought. You click. You read. And suddenly, the comfortable universe you trusted starts to fracture at the edges. The object in question is 3I, Atlas, and for months, astronomers had been calling it an interstellar comet. Just another icy visitor from beyond our solar system. Nothing to see here. They implied. Move along. But comets have habits. They follow rules. Ice warms near the sun. Gas erupts. Dust follows. Tails stream away on solar radiation like cosmic windsocks. It's physics 101, the kind of material we've understood since before your grandparents were born. Except 3I, Atlas, doesn't behave like it signed that contract. When Hubble turned its gaze toward this visitor in late July, scientists expected the familiar script. A fuzzy sphere of dust and ice, maybe a few jets, pointing in reasonably predictable directions, a tail obediently flowing away from the sun. Standard comet behavior, paint by numbers. But what Hubble captured instead made even seasoned astronomers pause and quietly mutter the kinds of words you don't hear on family-friendly science channels. The images showed something wrong. The dust distribution wasn't behaving. The geometry of the jets, those plumes of gas and particles, wasn't following the usual choreography. And most bizarrely, there were features pointing toward the sun. Sunward. Hold that image in your mind. It's like standing in a hurricane and watching the rain fall upward into the storm. That's the level of wrong we're talking about. Now, before this starts to sound like clickbait alien folklore, let me be clear. The data is real. The observations are strong. Hubble doesn't lie. And neither does its younger, sharper sibling, the James Webb Space Telescope. Two of the most advanced instruments humanity has ever placed in space, and both are whispering the same uneasy message. Something about 3I, Atlas, doesn't add up. The scientific community is being cautiously diplomatic, as they should be. NASA and the European Space Agency still officially classify it as a comet. They point to the hyperbolic orbit, the coma, the dust, all the features that look comet-like. And they aren't wrong to be conservative. Science demands extraordinary evidence for extraordinary claims. And right now, we're in that uncomfortable middle zone, where the evidence feels extraordinary, but the language to describe it is still being written. But here's where it gets interesting. And by interesting, I mean the kind that keeps astronomers awake at 3:00 a.m., staring at spreadsheets until their eyes sting. The jet structures aren't merely unusual, they show a symmetry that natural processes rarely, if ever, produce so cleanly. The chemical composition, seen through Webb's infrared vision, looks unlike anything we normally associate with solar system comets. And the alignment. Some researchers are running odds that make winning the lottery look like a safe investment. Enter the controversial voices, the ones willing to say out loud what others only think in private. Avi Loeb, the Harvard astrophysicist known, famous or infamous, depending on who you ask, for suggesting Oumuamua might have been artificial, is now turning his attention to 3I. He isn't claiming little green men, not exactly, but he is asking the uncomfortable questions. Questions like, what would we expect to see if an object weren't entirely natural, and how would we know the difference? The mainstream establishment pushes back, as it should. Skepticism is the immune system of science, protecting it from infection by wishful thinking and wild speculation. They argue that unusual doesn't mean artificial, rare doesn't mean impossible, and simply because we haven't seen something before doesn't mean nature can't make it. Those are valid points, and they deserve real weight. But here's the thing that keeps nagging at me, the thing that makes this story so hard to put down. Every time we think we've seen the full range of what the universe can do, it throws a curveball. Black holes were once impossible. Exoplanets were once science fiction. The accelerating expansion of the universe didn't make sense until it did. The cosmos has a habit of being stranger than our best theories predict. So what are we looking at here? Is 3I, Atlas, just a garden-variety interstellar comet, a weird one, with quirks we haven't catalogued yet? Is it an entirely new class of object, something that forces us to update our taxonomy of cosmic bodies? Or, and here's where things become truly unsettling, is it something else altogether? Something that challenges not just our comet models, but our assumptions about what can travel between the stars? The answer matters more than you might think, because if this is just a comet, even a strange one, then it's a beautiful scientific puzzle, a message about conditions in other stellar systems. But if it's something more, if even a fraction of the speculative ideas contain truth, then we're not merely updating textbooks. We're rewriting the entire conversation about our place in the universe. Over the next several parts, we're going to go deep into the data, the anomalies, the theories, and yes, the wilder edges of speculation. We'll look at what Hubble and Webb actually saw, what it means, and what it might mean. We'll hear from believers and skeptics, mainstream and fringe. And by the end, you'll have enough to decide for yourself what you think is happening here. But I'll warn you now, once you see what I'm about to show you, you may not look at the night sky the same way again. Part 2. Hubble's latest imagery and morphologies. The date was July 21st. Liangtianling Arshiwu, somewhere in low Earth orbit. Hubble was doing what it does best, staring at things that refuse to make sense. Its target was 3I, Atlas, and the images it captured that day became the foundation for everything that followed. Every argument, every theory, every late-night debate in astronomy departments worldwide traced back to these frames of light. At first glance, what Hubble saw looked familiar. There was a nucleus, the solid core, wrapped in a fuzzy cloud of dust and gas called a coma. That cocoon is standard comet behavior. When surface ice warms under solar radiation, it doesn't melt, it sublimates, turning from solid to gas, dragging dust along with it. The result is a diffuse envelope that makes comets look soft and blurred through telescopes, like they're wrapped in cosmic cotton candy. But the devil lives in the details. And the details here were devilish. The shape of the dust cocoon wasn't the usual, roughly spherical haze astronomers expect. Instead, Hubble caught something closer to a teardrop, with material distributed in a way that hinted at complexity beyond simple, uniform outgassing. Imagine inflating a balloon, except it doesn't expand evenly. It develops a point, a direction, a subtle insistence that it wants to go somewhere. Then there were the jets. Oh, the jets. Most comets have them fountains of gas and dust erupting from active regions, typically where sunlight finds exposed ice. On a typical comet, jets are messy. They point in directions dictated by irregular shape, patchy ices, chaotic rotation, nature's graffiti, untidy but explainable. But the jets on 3I, Atlas, showed structure, not the accidental structure you get from random turbulence, the kind that makes you tilt your head and wonder. Multiple jet features emerged in patterns some observers described as suspiciously regular. Now, slow down. Natural processes can absolutely create patterns. Crystals form perfect hexagons. Snowflakes build six-fold symmetry. Nature loves geometry when conditions allow it. The real question is whether the conditions were right here or whether we're seeing something outside the statistical norms of natural jet formation. And this is where things get foggy, because it isn't just one odd feature. It's multiple anomalies arriving together in the same object. That's where probability becomes interesting. Researchers used Hubble's imaging to estimate the nucleus size based on reflected light and the dust distribution. They placed it somewhere between a few hundred meters and several kilometers across. A wide range, yes, but enough to say we're not dealing with a pebble or a speck. This is something substantial, big enough to have mass, gravity, presence. What especially struck astronomers was the lack of a classic comet tail. You know the iconic image? Bright head. Long, flowing tail streaming away from the sun, the look that lives in textbooks and childhood posters. 3I, Atlas, had dust. It had gas. It had activity. But the distribution refused to cooperate with expectations. Some images suggested material pointing in directions that didn't align with solar wind pressure or radiation pressure, the twin sculptors that normally carve comet tails into their familiar shapes. This is where the term anti-tail enters the conversation. Exactly what it sounds like, a tail that seems to point toward the sun instead of away. Anti-tails aren't impossible. Under specific geometry, dust can lag behind the orbit and create an illusion that looks sunward. Astronomers have seen anti-tails before, but the ones on 3I, Atlas, if that's what they were, seemed more pronounced, more persistent than the fleeting sunward effects typically reported. Hubble also captured evidence of what researchers called wobbling jets, structures that shifted during the observation window. That could suggest a nucleus rotating on an irregular axis, tumbling like a poorly thrown football. Irregular rotation is common in small bodies, so alone it wouldn't shock anyone. But stacked with everything else, it added another layer to an already complicated portrait. The dust distribution told its own story. In ordinary comets, dust gets pushed outward by gas pressure, then shaped by sunlight, creating patterns that depend on particle size. Bigger particles hang closer in. Smaller particles get pushed farther out, forming gradients astronomers can model with decent accuracy. But the dust around 3I, Atlas, wasn't following that familiar gradient. It was improvising, distributed in ways that suggested either unusual particle properties or forces at play beyond the standard solar wind and radiation pressure model. Hubble's observations were rich, but they had limits. Hubble works primarily in visible and ultraviolet light, great for dust and certain gas species, but not ideal for the infrared, where many molecular fingerprints hide. That's where the James Webb Space Telescope enters, seeing wavelengths invisible to Hubble and revealing chemical secrets in the warm infrared glow of the coma. But before we step into Webb's findings, sit with what Hubble showed us. An object that looks like a comet, acts somewhat like a comet, but refuses to fully commit to the role. Like an actor who knows every line, yet delivers them with timing just strange enough to make you wonder if they're improvising. The performance is familiar and yet unsettling, and that unease, that sense that something doesn't quite fit, is exactly where the real investigation begins. Part 3. The JWST Spectral Surprise. Carbon dioxide dominance. If Hubble gave us the portrait, Webb gave us the fingerprints, the chemical signature that might crack the case wide open. And what a signature it is. When Webb turned its infrared eyes toward this visitor, it revealed something that made cosmic chemists do a double take. A coma dominated by carbon dioxide to a degree rarely, if ever, seen in comet observations. Let's slow down and explain why that matters. When we study comets, we're studying time capsules, dirty snowballs stored in deep cold for billions of years, preserving chemical conditions from their birth. The standard comet recipe includes lots of water ice, because water is abundant, plus a mix of other frozen gases, carbon monoxide, methane, ammonia, and yes, carbon dioxide. But the key word is mix. Water usually dominates. It's the main voice in the choir of volatiles. 3I, Atlas, apparently didn't get that memo. Webb's spectra suggested a coma where carbon dioxide was the dominant species, with a CO2 to water ratio among the highest ever recorded. Not a slight preference. Reversal. Now, don't jump to the sinister conclusion. Let's consider what nature can do. Ice ratios depend on where and when an object formed. Bodies assembling far from their star can retain more volatiles. Carbon dioxide freezes under different conditions than water, so a particular temperature regime might favor it. There's also the cosmic ray factor. Interstellar space isn't empty, it's irradiated. High-energy particles from distant cataclysms slam into icy bodies, breaking bonds, rearranging molecules, creating compounds that wouldn't form as easily in calmer places. Imagine leaving a block of ice inside a silent particle accelerator for millions of years. You'd expect some chemical strangeness. An object wandering between stars for ages could accumulate modifications that make it stand out from solar system natives. But here's where it gets tricky. Cosmic ray processing is real, well studied, well understood. And yet, there are limits to what it can explain. The degree of carbon dioxide enrichment in 3I, Atlas, pushes against the edge of what current models comfortably predict. Not impossible. Not even close. But eyebrow-raising enough that multiple teams are running simulations in a quiet frenzy to see whether natural processes alone can reproduce the observations. And Webb's technique is precise. Infrared light reveals molecular vibrations, how atoms jiggle and sway when they absorb energy. Each molecule has its own vibrational fingerprint. Water vibrates at certain frequencies, carbon dioxide at others, carbon monoxide at still others. By reading which frequencies are absorbed or emitted by the coma, scientists can identify not just what's present, but in what proportions. It's like reconstructing a cake recipe by analyzing the light reflecting off the frosting. Impossible for human eyes, straightforward for the right instruments. And what Webb saw in 3I, Atlas, was unmistakable. A forest of strong carbon dioxide lines, clear and confident, with water signatures present, but quieter. This wasn't marginal. This wasn't tentative. It was a loud chemical statement. Carbon dioxide dominates this coma, so the question becomes, why one interpretation says this object formed in an environment unlike our solar system's comet factories, a place where CO2 ice was simply more available or more easily retained. Different stellar systems can have different chemical inventories. Their parent molecular clouds vary. Nearby supernovae can seed regions with different elements. Formation histories diverge, so an interstellar visitor could, in theory, to arrive with chemistry that looks alien, not artificial, just unfamiliar. Another angle focuses on processing during its interstellar journey. Radiation doesn't only scramble molecules randomly, it can drive specific reactions. Cosmic rays striking water ice can split it apart. Under certain conditions, fragments can recombine with carbon to form carbon dioxide over immense timescales. Surface layers could shift, enriching CO2 while reducing water, but some researchers lean toward a more radical framing. What if this isn't a traditional comet at all? What if it's a category we haven't named yet? We already had to expand our vocabulary with objects like Oumuamua, which showed odd behavior without a classic coma. Maybe the universe's small body population is broader than our solar system ever trained us to expect. Carbon dioxide dominance also changes how we interpret behavior. CO2 sublimates differently than water, so outgassing patterns can be more vigorous in certain regimes, potentially shaping jets in unusual ways. Different volatiles entrain dust differently too, which could influence the dust structures Hubble observed. And yet, despite all these natural explanations, a nagging question remains. Why is this one so different? Why? Out of all the interstellar visitors we might detect, do we get one with such an extreme chemical profile? Is it because objects like this are common, and we simply lack the tools to see the difference until now? Or is 3I, Atlas special, an outlier among outliers NASA and ESA? Scientists are cautious, as they should be. They acknowledge unusual chemistry. They explore multiple hypotheses, but they are not ready to call it anything beyond a very interesting comet with atypical composition. And honestly, that restraint is correct. Science moves by careful accumulation, not by fireworks. But the data point is weird, compellingly weird, and it's about to get weirder. Part 4, the mainstream counterpoint. NASA and ESA still call it a comet. Let's breathe and ground ourselves in the official stance. because in the rush toward anomalies, it's essential to remember the people with the best expertise and the best access still classify this as a comet, not a probe, not an artifact, not a cosmic riddle beyond comprehension. A comet. Unusual. Yes, but natural. NASA's statements describe 3I Atlas as an interstellar comet, emphasizing activity consistent with volatile outgassing as it approaches the Sun. They point to the hyperbolic orbit, a path that brings it in from interstellar space and will sling it back out again. That's exactly what you expect from a visitor that did not originate here. A one-time pass, a transient guest. Given escape velocity by gravitational interactions in its home system, the European Space Agency echoes this view. They point to the coma, the defining hallmark of cometary activity. They note jets, unusual in configuration. Yes, but still explainable through sublimation of volatiles from the nucleus surface. The carbon dioxide signatures, interesting compositional variation, not necessarily incompatible with natural formation. And this conservative approach isn't stubbornness. It's how science is designed to protect itself. You start with the simplest explanation that fits, and only move to more exotic ones when the simple model collapses. This is Occam's razor in motion. A comet with odd chemistry requires fewer assumptions than a technological artifact from an unknown civilization. So, let's walk the anomalies through the mainstream lens, one by one. Symmetric jets, natural comets, can produce multiple jets. Under certain rotations and surface conditions, they can appear surprisingly regular. Imagine a potato-shaped nucleus rotating on a tilted axis with active patches placed just so. From the right viewing geometry, jets can line up in ways that look almost designed, even when they arise from messy physics. Geometry emerging from chaos is, ironically, very natural. The sunward features antitails aren't unprecedented. When dust lingers along an orbit and Earth's perspective shifts, older dust can create optical effects that appear to point toward the sun. Rare. Yes. Geometry dependent. Yes. But documented. The CO2 dominance is the tougher one. Even conservative scientists admit it's unusual. But unusual isn't unnatural. Our sample size of well-characterized interstellar objects is tiny. If anything, we might be mistaking local solar system norms for universal rules. Maybe high CO2 ratios are common elsewhere, and we're only now learning how diverse comets can truly be. The mainstream position also highlights what we haven't detected. No radio transmissions. No optical flashes indicating power sources. No clear spectroscopic signatures of refined industrial materials. No trajectory corrections beyond what outgassing could plausibly produce. If this were a probe, they argue, we'd expect at least one unmistakable techno-signature, and the absence of that is, to them, strong evidence of a natural object. They also warn against premature speculation. History is full of false alarms. Pulsars were once joked about as alien beacons. Oumuamua became a cultural flashpoint. Again and again, the universe has eventually offered natural explanations. It isn't obligated to be boring, but it also doesn't need alien artifacts to be astonishing. Nature can produce outcomes that feel purposeful while simply obeying physical laws in complex ways. There's also observational bias. We notice what's strange. We study anomalies more intensely than ordinary objects. If 3I Atlas were perfectly average, it wouldn't receive this level of scrutiny. A normal comet becomes a footnote. An odd one becomes a magnet. So we select for weird, and then act surprised when we find it. Science demands hypotheses be tested against alternatives. The comet hypothesis is testable, falsifiable, and so far, not falsified. It predicts volatile outgassing, dust production, activity changes with solar distance, and broadly icy body chemistry. 3I Atlas checks those boxes, even if it checks them in unusual handwriting. But here's what bothers me, and what quietly bothers a growing number of researchers, even within the mainstream. At what point does quirky become genuinely anomalous? If one thing is weird, fine. If two things are odd, interesting. But we're stacking anomaly after anomaly, jets, chemistry, dust distribution, alignment-like features, and at some point, the probability of all those unlikely things clustering in one object starts to strain the imagination. The mainstream response is simple and sober. We need more data, long-term monitoring, better spectroscopy, radar, if it comes close enough, infrared thermal work. Exhaust every natural explanation before leaning into exotic conclusions. And they're right. The burden of proof should be high. Science isn't about sprinting to the most thrilling answer. It's about arriving at the correct one, slowly, carefully. The fact that NASA and ESA still call it a comet doesn't mean blindness. It means discipline. But skepticism cuts both ways. It's fair to ask whether the caution that prevents premature conclusions might also delay recognition of something truly unprecedented. That's the tightrope of good science, staying open enough to recognize the new, while filtering out the noise of false alarms. So which side of that line does 3I, Atlas, fall on, and how will we know? Part 5, where the standard model fails. We've heard the careful official line, and it may be correct, but science also demands we examine where models fray, where predictions don't quite match observation, because those gaps are where new understanding often begins. And here, there are gaps, real ones. Let's begin with the jets, the most visually dramatic anomaly. Standard comet physics says jets form when sunlight heats buried ice beneath dust layers. As ice sublimates, pressure builds, then vents, launching gas and dust in fountains. The direction depends on where active regions are, and on a tumbling, irregular nucleus. You expect a kind of chaotic randomness. What observers reported for 3I, Atlas, doesn't quite match that expectation. Multiple jets, appearing at seemingly regular, angular spacing, holding structure across observation windows, showing an organization that typical outgassing from a lumpy, rotating body rarely displays so cleanly. Now, seemingly matters. We're interpreting imaging data, not reading a blueprint. But multiple independent observers have noted the geometry. Could rotation explain it? Maybe. If the nucleus spins just so, if active patches are symmetrically placed, if Earth's viewing angle aligns just right, then yes, you could get organized-looking jets. But that is a lot of ifs. Each is plausible alone. Stacked together, probability starts to push back. Then there's the axis alignment question, and this is where statistics get slippery. Some analysts suggest the rotational axis shows improbable alignment with trajectory, or with the sun. If true, it's strange, because angular momentum doesn't care about your velocity vector. A tumbling comet should tumble however its history leaves it. The counterargument is important. With enough parameters and enough definitions of alignment, you can always find something that looks meaningful. Data can be tortured into confession. Humans are pattern-seeking by nature. We'll find structure in randomness if we stare long enough. So we have to be careful. But then we reach the dust distribution, and that's where reconciliation gets hardest. Dust should follow predictable patterns. Solar radiation pressure pushes small particles faster than big ones. Gravity keeps everything anchored near the nucleus. Solar wind adds its own sculpting. Put it together and you get equations that describe how dust should spread. But 3I, Atlas's dust appears, disobedient. Hubble showed features that don't neatly match standard model outputs. Some researchers suggest clumping or streaming that implies additional forces or unusual particle properties. Others argue it's normal dust, seen under unusual geometry. Perspective can masquerade as anomaly. And here I need to acknowledge something quietly and honestly. I'm not a professional astronomer. I don't have the raw data or the full simulation suites. I'm synthesizing what's published and what experts are debating, trying to give you a fair sense of where the uncertainty lives. And uncertainty does live here, substantive uncertainty about whether conventional comet physics fully closes the gap, or whether something extra is required. The energy budget is another point of contention. What researchers have observed on 3I Atlas doesn't quite fit that random expectation. Multiple jets appear at seemingly regular angular intervals, holding their form across observation windows, almost like a slow metronome ticking in the dark, showing a level of organization that, simple outgassing from a battered, irregular body wouldn't typically maintain. Now, I need to be careful, because seemingly regular is doing a lot of work in that sentence. We're talking about interpretations of imaging data, not precise measurements with neat error bars. But multiple independent observers have noted the unusual geometry. Could rotation explain it? Maybe. If the nucleus is spinning on a particular axis, and if the active ice patches happen to be distributed symmetrically, and if the viewing geometry from Earth happens to align just right, then yes, you could get jets that appear organized. But that's a lot of ifs. Each one is plausible on its own. But stacking coincidences is where probability starts to push back. Then there's the axis alignment question. And this is where things get statistically murky. Some analysts claim the orientation of 3I Atlas's rotational axis shows an improbable alignment with its trajectory, or with the Sun. If true, that would be bizarre, because there's no obvious mechanism for such alignment to occur naturally. Angular momentum doesn't care about your velocity vector or solar direction. A tumbling comet should tumble in whatever orientation its formation and subsequent collisions left it with. The counterargument is that we're cherry-picking alignment from noise, with enough parameters to measure and enough ways to define alignment. You can always find something that looks meaningful if you torture the data enough. This is a real concern in any field dealing with complex observations. Human brains are pattern-seeking machines, and we'll find structure even in randomness if we stare long enough. But let's talk about the dust distribution, because that's where the observations become hard to reconcile with standard models. Comet dust is supposed to follow predictable patterns based on particle size, composition, and the forces acting on it. Solar radiation pressure pushes small particles faster than big ones, creating a size-sorted distribution. Gravity from the comet pulls everything toward the nucleus. Solar wind adds another layer of influence, like a faint, invisible current slipping past like starlit tidewater. Put it all together, and you get equations that describe how dust should spread out in space. 3I Atlas's dust doesn't seem to be reading from that playbook. The distribution Hubble recorded showed features that don't match the standard model's predictions. Some researchers suggest the dust is clumping or streaming in ways that require additional forces, or unusual particle properties. Others argue the observations are being misread, that what looks like an anomalous distribution is actually a normal distribution, viewed under unusual geometric conditions. Here's where I need to acknowledge my own limitations. I'm not a professional astronomer, and I don't have access to the raw data or the sophisticated models these researchers are running. I'm synthesizing what's been published and what experts are debating, trying to give you a fair picture of where the uncertainty lies. In the quiet between pixels and assumptions, and there is uncertainty real. Substantive uncertainty about whether the observations can be fully explained by conventional comet physics, or whether something additional is needed. The energy budget is another point of contention. When a comet outgasses, it loses energy. That energy comes from solar heating converting ice to gas. You can calculate how much energy is available based on solar flux, surface area, and ice composition. You can then estimate how much gas and dust that energy can drive off the surface. The numbers should balance. Input equals output. Thermodynamics doesn't take vacation days. Some analyses of 3I Atlas suggest the observed activity level is inconsistent with the energy budget you'd expect from solar heating alone, especially given its distance from the Sun and the unusual composition. If true, that would imply either an additional energy source which is troublesome for a natural body, or errors in how we're estimating the activity level or the energy input. Neither option is comfortable. Of course, there are ways to patch the gaps. Maybe the surface has unusual reflective properties that concentrate heat. Maybe there's residual internal heat from radioactive decay. Maybe subsurface ice reservoirs are releasing stored energy. Each patch makes the model more complex, adds more free parameters, and reduces its predictive power. At some point, you're not explaining the data so much as accommodating it with increasingly baroque adjustments. Polarization measurements add another wrinkle. Light scattered by dust becomes polarized, and the degree of polarization tells you something about dust particle size and composition. The polarization observations of 3I Atlas apparently show variations that some interpret as anomalous. Again, the mainstream pushback is that polarization is complicated, depends on viewing geometry, and can be tricky to interpret definitively, but it's another data point that doesn't quite sit inside the standard picture. Brightness variations over time are also puzzling. Comets typically get brighter as they approach the sun and dimmer as they recede. Following a predictable curve based on increased activity from solar heating, 3I Atlas showed brightness changes that some observers say don't match that expected curve. Could be rotation bringing different surface features into view. Could be regular outgassing. Could be normal cometary behavior that looks weird because of incomplete observations. Or could be something else. What frustrates me about this whole situation is the lack of definitive answers. We're drowning in May, and could be, and possible. Every anomaly has a potential natural explanation, but none of the explanations are slam dunks. It's like a court case where the prosecution has circumstantial evidence piled to the ceiling, but each piece individually could be explained away. The question is whether the cumulative weight of all these anomalies, taken together, pushes the standard model below acceptable thresholds. Different researchers will answer that question differently based on their prior expectations, their tolerance for uncertainty, and their philosophical stance on when to abandon established models. The conservatives say the standard model is flexible enough to accommodate these observations with minor adjustments. The radicals say we're seeing something genuinely new that requires new physics or new categories. And the truth, as is often the case, probably lies somewhere in the messy middle. But here's what we can say for certain: 3I Atlas is pushing our models. In a gentle but relentless way, it's testing the limits of what standard comet physics can explain. And whether it ultimately stays within those boundaries or breaks through them, it's forcing astronomers to think more carefully about what they actually know versus what they've assumed. And that, regardless of the final verdict on this object, is scientifically valuable. The question is, what happens when you keep pushing? When do bends become breaks? Part 6. Jet symmetry and rotation geometry, natural or engineered. All right, let's get specific about the weirdest feature of 3I Atlas, the thing that makes even skeptical astronomers pause and stare at their screens a beat longer than usual: the jets. Not just that they exist, but how they're arranged, how they behave, and what that might mean if you're willing to entertain uncomfortable possibilities. Imagine you're looking at a comet through a powerful telescope. You expect to see chaos. These are lumpy, irregular chunks of ice and rock that have been battered by billions of years of cosmic collisions. Their surfaces are pockmarked, cratered, asymmetric. When sunlight hits and ice starts subliming, gas erupts from wherever ice happens to be exposed. Maybe there's a jet coming off what looks like the North Pole, another from a crater on the equator, a third from some random spot on the southern hemisphere. There's no organization, no pattern. It's geology and thermodynamics having a messy conversation. But what if, instead of that expected chaos, you saw 3 jets emerging from the nucleus at roughly equal intervals: 120 degrees, 140 degrees, 260 degrees, spaced like they were planned. Like someone sat down with a protractor and said, let's put the vents here, and here for optimal distribution. That would be weird. Right. That would make you wonder whether what you're looking at is entirely natural. Now, before the engineers in the audience start sending me angry emails, let me be clear about what we actually know versus what people are speculating. The reports of perfect jet symmetry and 3I Atlas are not universally accepted. Different observation teams see different things depending on when they observed, from what angle, and with what instruments. Some see clear triple jet structures, others see more chaotic emission. The data is messy, which is astronomy's default state. But let's play this out. Suppose, for a moment, that the symmetry is real, that we're genuinely seeing jets arranged in an organized pattern. How do we explain that naturally? Well, crystals do it all the time. Water freezing into snowflakes produces 6-fold symmetry from random molecular interactions following physical laws. Basalt columns form hexagonal patterns when lava cools. Nature loves symmetry when the conditions favor it. For a comet nucleus to produce symmetric jets naturally, you'd need a symmetric distribution of volatile ices, which could happen if the body formed under conditions where ice deposition was uniform. You'd need the rotation axis aligned just so, which is just a matter of angular momentum. You'd need surface features that channeled outgassing in specific directions, which topography could provide. Stack enough compatible conditions together, and sure, you could get organized jets naturally. But here's the catch. Each of those conditions is somewhat unlikely on its own. Ice distribution on most comets is anything but uniform. Rotation axes point in random directions. Surface topography is chaotic. Getting all of these factors to line up just right in one object is possible, but improbable. And improbable isn't impossible, but it makes you wonder whether there's a better explanation. The alternative, the elephant in the room, that everyone's thinking about, but most scientists won't say out loud, is that the jet symmetry isn't accidental, that it's functional, that if you were designing something to move through space using controlled gas emissions, you'd want symmetric thrust vectors to maintain stability and predictable trajectory. You'd place your vents at regular intervals to avoid tumbling. You'd orient them to produce the desired acceleration without wasting fuel on random directions. I want to be absolutely clear here. I am not claiming 3I Atlas is a spacecraft. I'm not even suggesting it probably is. What I'm doing is laying out the logic chain that makes some researchers, including respected scientists with decades of experience, willing to at least consider the possibility as a hypothesis worth investigating rather than dismissing out of hand. The rotation geometry adds another layer to this puzzle. Objects in space rotate because of how they formed and whatever collisions they've experienced. That rotation should be stable and less disturbed by external forces. But some observations suggest 3I Atlas might be rotating in ways that seem unusually stable or oriented relative to its trajectory. Again, this could be confirmation bias, seeing patterns in noise, or it could be a clue. Let's use an analogy. Imagine you find a rock on the beach. It's roundish but irregular, clearly shaped by waves and time. Natural, no question. Now imagine you find a rock that's almost perfectly spherical, polished, smooth, with what looks like regularly spaced indentations around its equator. Still could be natural weird erosion, strange mineral composition. Who knows, but your brain would start asking questions. You'd want to look closer. You'd want to rule out human manufacture before concluding it's a geological fluke. That's where we are with 3I Atlas. The jet patterns could be geological flukes, cosmic coincidences, the result of specific but entirely natural formation conditions. And probably, most likely, they are, but the pattern is geometric enough, regular enough, that it triggers our pattern recognition systems, makes us want to look closer, makes us reluctant to just shrug and move on. Some researchers have calculated the probability of randomized distribution producing the observed symmetry. These calculations are fraught with assumptions, many of which can be challenged. But they generally come up with small numbers, not astronomically small, not winning the lottery small, but small enough to notice. 1 in 100 type odds, maybe 1 in 1,000 depending on the model. Which brings up the frequency argument. If the odds are 1 in 1,000 and we've observed thousands of comets, then seeing one with unusual symmetry is exactly what we'd expect. Rare events happen. That's what rare means. It doesn't mean impossible. It doesn't mean artificial. It just means most of the time you don't see it. But sometimes you do. The counter-argument focuses on the cumulative probability. Sure, symmetric jets might be 1 in 1,000, but symmetric jets plus unusual composition plus odd dust distribution plus brightness anomalies plus trajectory alignment, multiply those probabilities together, and suddenly you're in much rarer territory. You're going from, we'd expect to see this eventually, to, this is genuinely surprising. Of course, you can also argue that we're cherry-picking anomalies and multiplying probabilities inappropriately. Not every unusual feature is independent. Some might arise from the same underlying cause. And if you look at any object closely enough, you'll find things that seem improbable after the fact. This is the problem with posterior probability. Everything that happened was unlikely before it happened. Specificity creates the illusion of impossibility. So where does that leave us? With jets that are either natural and unusual, or possibly indicating something worth investigating further, with rotation that's either normal and we're over-interpreting it, or aligned in ways that deserve explanation with geometry that's either coincidental or meaningful. And we don't yet have enough data to definitively say which. What I can tell you is that professional astronomers are taking this seriously. Multiple research groups are running detailed simulations, trying to reproduce the observed jet patterns with natural processes. They're testing different nucleus shapes, different ice distributions, different rotation states. If they can find a model that naturally produces what we see, that would be powerful evidence for the conventional interpretation. If they can't, well, that's when things get really interesting. And interesting in astronomy often means uncomfortable. Part 7. Rare metal and molecular signatures. Now, we need to talk about the chemistry. Because if the physical behavior of 3I Atlas is raising eyebrows, the chemical composition is making some researchers' heads explode. We've already discussed the carbon dioxide dominance, which is weird but potentially explainable. But that's just the beginning of the chemical story. There are reports, preliminary and contested, of molecular signatures that have no business being in a normal comet, and chief among these is nickel tetracarbonyl. For those who slept through chemistry class, nickel tetracarbonyl is exactly what it sounds like. One nickel atom bonded to 4 carbon monoxide molecules. It's a nasty piece of work, highly toxic, volatile at relatively low temperatures. And here's the kicker, it almost never shows up in nature. On Earth, it's primarily known as an industrial compound used in nickel refining and as a catalyst in certain chemical processes. Finding it in space, especially in a comet, would be like discovering a plastic bottle on Mars. Possible. Maybe. Expected. Absolutely not. The detection reports come from spectroscopic analysis by amateur astronomers and a few professional teams who noticed unusual absorption lines in the object's spectrum that don't match common cometary molecules. When they ran the lines through spectral databases, nickel tetracarbonyl came up as a possible match. Now, and this is crucial, these detections are not confirmed by mainstream facilities. They're preliminary, based on limited data, and subject to alternative interpretations. Spectral lines can overlap. Instruments can have artifacts. Confirmation bias can make you see what you expect to find. But let's suppose, just for argument's sake, that the detection is real. How the hell does nickel tetracarbonyl end up in an interstellar comet? Well, you need nickel, which is common enough in meteorites and cosmic dust. You need carbon monoxide, which is abundant in molecular clouds. Bring them together under the right temperature and pressure conditions. Add a dash of catalytic surface chemistry, and theoretically, you could synthesize nickel tetracarbonyl in space. It's not impossible. Astrochemistry has produced stranger molecules in laboratory simulations of interstellar conditions. The problem is that nickel tetracarbonyl is unstable. It breaks down under ultraviolet radiation, which space has in abundance. It decomposes at relatively warm temperatures, which an object approaching the sun would experience. For it to survive in detectable quantities would require either continuous production, which implies active chemistry happening on or in the nucleus, or storage in protected reservoirs that only recently opened up. Both scenarios are plausible, but add complexity to an already complicated picture. Other unusual molecular detections have been reported. Methanol, hydrogen cyanide, formaldehyde. Individually, none of these are shocking. All have been found in comets before, and all are products of ice chemistry in cold, dark environments. But the proportions are off. The ratios don't match what solar system comets show. It's like tasting a familiar dish, but the spices are all wrong. Recognizable ingredients in an unfamiliar recipe. Methanol, for instance, is often used as a tracer for certain formation conditions. High methanol relative to water suggests ice processing in very cold environments, possibly in interstellar clouds before the comet ever joined a stellar system. 3I Atlas shows elevated methanol, which fits the narrative of an object that spent eons drifting between stars, soaking up molecular cloud chemistry. Hydrogen cyanide is another interesting case. It's a key component in prebiotic chemistry, one of the building blocks that might have seeded early Earth with the ingredients for life. Finding it in an interstellar visitor would support theories that life's precursors came from space, delivered by impacts. It would also tell us that the chemical conditions for life might be common across the galaxy, not unique to our solar system. But here's where the fringe theories start creeping in. If you're looking for evidence of artificial origin, unusual chemistry could be interpreted as contamination from industrial processes or fuel residues. Nickel, tetracarbonyl, after all, is used in certain types of chemical propulsion systems and refining operations. If you were a civilization trying to move a large object through space using sublimation-based thrust, you might select chemical compositions to optimize performance. You might include metals for structural strength or catalytic properties. I need to stop right here and emphasize this is speculation piled on speculation, built on a foundation of unconfirmed observations. We have no credible evidence that 3I Atlas is artificial. None. What we have are unusual chemical signatures that might point to exotic natural processes, or might be artifacts of observation, or might require us to expand our understanding of interstellar chemistry. The water detection is worth mentioning, because it complicates the narrative. Early analyses suggested minimal water, which fed the whole "this is weird" story, but subsequent observations with different instruments found water signatures in the ultraviolet, suggesting water is present, just not dominant. This is actually reassuring for the natural interpretation, because a complete absence of water would be truly bizarre for an icy body. Water is everywhere in space. Finding an object with ice but no water would be like finding sand with no silicon, so the very presence of water, even in modest trace, pulls the story back toward the natural. But this chemistry debate highlights a deeper challenge in studying visitors like this. We're trying to understand complex dynamic systems using snapshots and limited data. Imagine trying to figure out what's in someone's kitchen by smelling the air from their driveway. You might catch a ribbon of garlic, a soft hint of coffee, maybe something faintly burning at the edges. But reconstructing the full inventory, knowing exactly what's cooking, requires getting inside, which we can't do with an object millions of kilometers away, moving at interstellar velocities. Spectroscopy is incredibly powerful, but it has limits, and those limits matter. You only see what's in the gas phase, what's subliming, venting, or being ejected from the surface. The bulk composition of the nucleus, the deep interior chemistry, remains hidden in cold layers we can't peel back. Surface processes, solar radiation, and interaction with the solar wind can all modify coma chemistry, making it an imperfect proxy for the object's original composition. It's like trying to understand a book by reading the dust jacket. You'll get clues, maybe even a mood, but you might miss the actual story. Different research teams are approaching this chemical mystery from different angles. Some are running laboratory experiments, trying to recreate interstellar chemistry conditions and see what molecules emerge under that long, patient darkness. Others are developing models of how cosmic ray processing affects ice chemistry over millions of years. Still others are searching for similar signatures in other interstellar objects, trying to determine if 3I Atlas is unique or part of a wider population. What nobody wants to say out loud, but everybody's thinking, is that unusual chemistry could be the smoking gun, not for alien technology necessarily, but for something genuinely new in our understanding of cosmic chemistry. Maybe there are formation environments we haven't considered. Maybe interstellar processing creates chemical compositions we once assumed were unlikely or rare. Maybe the galaxy is chemically more diverse than our parochial solar system experience suggests, richer in recipes than we've ever tasted. Or maybe, just maybe, we're looking at something that didn't form naturally at all. But proving that would require extraordinary evidence. And so far, all we have are intriguing hints and uncomfortable questions. The chemistry of 3I Atlas is strange. No doubt, whether it's naturally strange or artificially strange remains one of the great unanswered questions of this whole affair. And the uncertainty, frankly, is the most scientifically honest position we can take right now. Part Wit. Fringe and academic speculation spectrum. Let me take you on a journey across the full landscape of interpretations for 3I Atlas, from the scientifically mainstream to the wildly speculative, because understanding this object means acknowledging the entire spectrum of possibilities, even the ones that make us shift in our seats. And I promise to be clear about where established science ends and imaginative conjecture begins, because conflating the two is how we end up with headlines that mislead rather than inform. At the most conservative end of the spectrum sits the hypothesis that 3I Atlas is exactly what NASA says. It is a natural interstellar comet with some unusual, but ultimately explainable, features. This interpretation requires the fewest new assumptions. Comets exist. Interstellar objects exist. Unusual chemistry exists. Put them together and you get 3I Atlas. End of story. Back to cataloguing exoplanets. Back to the steady rhythm of the sky. Moving slightly toward the exotic, we encounter the idea that this is a natural object, but one that represents a new category we haven't seen before. Maybe it's a hybrid body part asteroid. Part comet formed in conditions between the ice-rich outer regions and rocky inner regions of another stellar system. Maybe it's a fragment of a larger body destroyed by collision, explaining the unusual composition through selective vaporization during impact. Maybe it's a captured rogue planet or moon that got booted from its original system and spent billions of years being processed by cosmic rays. All natural, all within known physics, just requiring us to expand our taxonomy. To admit our old labels might be too small. Then there's the cosmic ray processing hypothesis, which takes center stage in several academic papers. This idea suggests that 3I Atlas spent an extraordinarily long time in interstellar space, potentially tens or hundreds of millions of years, being bombarded by high-energy particles from supernova remnants and active galactic nuclei. That radiation could drive exotic chemistry, alter isotopic ratios, create unusual molecular species, and modify surface properties in ways that make the object look different from solar system natives that haven't experienced such prolonged exposure. It's natural. It's physics, we understand. It just requires an extreme environment and an extreme duration time doing what time does best. Quietly rewriting matter. Now we start sliding toward the speculative fringe, but still within the realm of astrophysical plausibility. Some researchers propose that 3I Atlas could be a fragment of a pulsar planet, one of those bizarre worlds that orbit the remnants of exploded stars. These environments are bathed in intense radiation and magnetic fields, which could produce truly alien chemistry and physical properties. If such a fragment got ejected and wandered into our solar system, it might look like nothing we've ever encountered. Natural, yes. Normal? Absolutely not. Another fascinating hypothesis suggests electromagnetic interactions with the solar wind could explain some of the unusual behavior. Charged dust particles. Magnetic fields frozen into the nucleus. Plasma sheets forming around the coma. Subtle structures of electricity and magnetism threading through the dust like invisible silk. All of these could create forces and effects beyond simple gravity and outgassing. We've seen hints of electromagnetic phenomena in comets before, but usually subtle. If 3I Atlas has particularly strong electromagnetic properties, either from composition or from charged particle accumulation during its interstellar journey, that could manifest as unusual jets, unexpected accelerations, or aberrant dust distribution. Still natural. Still physics, just electromagnetics, rather than pure mechanics and thermodynamics. And now, dear viewer, we arrive at the territory where scientific caution gives way to provocative speculation. This is where figures like Avi operate, and love him or hate him. You can't deny he asks questions that linger. Loeb and other adventurous thinkers have proposed that we should at least consider the possibility that 3I Atlas exhibits features consistent with artificial origin or modification. Not definitely artificial, not probably artificial, but consistent enough that dismissing the idea without investigation would be intellectually lazy. What would artificial look like? Well, if you were a technologically advanced civilization trying to move a large object through interstellar space, you'd face certain engineering challenges. You'd need propulsion, which could come from controlled outgassing, essentially using the object itself as fuel. You'd need stability, which requires symmetric thrust. You'd need navigation, which might involve orientation control. You'd probably use readily available materials, which means ice and rock, the abundant components of any stellar system's debris. The result might look a lot like a comet, but with subtle regularities that natural chaos doesn't typically produce. This hypothesis doesn't require little green men piloting the object. It doesn't require faster-than-light travel or physics-defying technologies. It just requires engineering applied to cosmic-scale problem-solving. Moving asteroids or comets is something we humans are already contemplating for planetary defense and resource extraction. A civilization 1 million years older than us might have turned such operations into routine infrastructure maintenance. The way we maintain roads, only their roads are made of orbits. Of course, this raises the question, why? Why would anyone send a modified comet through interstellar space probe? Mission: waste disposal. Accident: deliberate seeding of stellar systems with life's building blocks. The motivations of a hypothetical alien civilization are, by definition, speculative. We can't even agree on why humans do half the things we do, let alone guess at alien intent. The most extreme interpretations veer into territory that's more philosophy than science. Some suggest 3I Atlas could be a Bracewell probe, a self-replicating artificial object designed to explore the galaxy over millions of years, using encountered materials to repair and duplicate itself. Others propose it's a derelict, the abandoned remnant of failed technology drifting through space like the cosmic equivalent of ghost ships on Earth's oceans. These ideas are unfalsifiable with current data, which makes them poor science, but excellent science fiction. What's important to understand is that the spectrum from conservative to fringe isn't a spectrum from smart to dumb, or rigorous to sloppy. It's a spectrum of epistemic risk tolerance. Conservative interpretations minimize the risk of being wrong by staying close to established knowledge. Speculative interpretations accept higher risk of error in exchange for potentially revolutionary insights. Both approaches can serve a purpose in the scientific ecosystem. If we keep their evidentiary weight in proper proportion, the mistake would be treating all positions on this spectrum as equally likely or equally evidenced. They're not. The natural comet hypothesis has vastly more supporting evidence and requires fewer leaps of logic than the artificial probe hypothesis. But minority positions aren't automatically wrong just because they're minority positions. Science has a history of initially rejected ideas that later became orthodoxy. Plate tectonics, heliocentrism, quantum mechanics all faced fierce resistance before acceptance. So where does 3I Atlas actually fall on this spectrum? Honestly, we don't know yet. The data is insufficient. The observations are incomplete. The models are uncertain. What we can say is that this object has properties that push it toward the unusual end of the natural range, making it worth careful study regardless of whether it's ultimately explained by known processes or requires new categories. The worst thing we could do is stop asking questions. The second worst thing would be to confuse questions with answers, or speculation with conclusion. 3I Atlas is a question mark flying through our solar system, and how we investigate that question will say as much about us as the eventual answer says about the object itself. Part 9. High-profile advocates and critics. Let's talk about the people behind this debate, because science isn't just data and equations. It's humans arguing about interpretations, defending positions, challenging assumptions, and occasionally throwing academic shade at each other in peer-reviewed journals. And few figures in astronomy inspire as much passionate response, both positive and negative, as Avi Loeb. Loeb is a professor at Harvard, former chair of the astronomy department, a prolific researcher with hundreds of publications, and more recently the public face of the maybe it's aliens hypothesis for unusual astronomical objects. He was the primary advocate for considering Oumuamua, the first confirmed interstellar object detected in our solar system, might be artificial rather than natural. That stance earned him widespread media attention. A book deal, a lot of criticism from colleagues, and a reputation as either a visionary willing to ask uncomfortable questions or a publicity-seeking contrarian undermining scientific rigor, depending on who you ask. Now, Loeb has turned his attention to 3I Atlas, and he's doing what he does best, pointing out features that don't quite fit standard models, and suggesting we shouldn't dismiss exotic explanations without serious investigation. In statements and writings about this object, he's highlighted what he sees as 8 specific observations that, in his view, are difficult to reconcile with natural comet behavior. These include the trajectory alignment, the unusual tail geometry, the symmetric jet patterns, the chemical composition anomalies, and several others. Loeb's argument isn't "this is definitely artificial." His argument is this is anomalous enough that we should seriously investigate the artificial hypothesis rather than assuming it must be natural. It's a subtle but important distinction. He's advocating for a particular approach to anomaly. Take it seriously, study it rigorously, and don't let preconceived notions about what's possible prevent you from considering what the data might actually be showing. His critics, and there are many, argue that Loeb is systematically underestimating the flexibility of natural processes and overinterpreting sparse data. They point out that every one of his 8 observations has potential natural explanations, even if those explanations require somewhat unusual but not impossible conditions. They note that by cherry-picking the most anomalous features and ignoring the many ways 3I Atlas behaves like a normal comet, you can construct a misleading narrative. Some of the pushback gets personal. There are whispers in the astronomical community about attention-seeking, about sacrificing scientific credibility for media coverage, about setting a bad example for younger researchers by legitimizing speculation that borders on pseudoscience. Other scientists have publicly stated that giving oxygen to the artificial hypothesis without extraordinary evidence is irresponsible, potentially undermining public trust in science and encouraging conspiracy thinking. But Loeb has defenders. 2 researchers who argue that science needs people willing to challenge consensus, who point out that history is full of dismissed ideas that later proved correct, who suggest that the harshness of the criticism says more about the field's conservative bias than about Loeb's arguments. They note that he's not claiming certainty, just advocating for serious investigation of a possibility that most researchers dismiss reflexively rather than analytically. The institutional response from NASA and ESA has been measured but firm. Both agencies maintain that their analysis of 3I Atlas is consistent with natural origin, that no technosignatures have been detected, and that while the object has unusual features, unusual is not synonymous with artificial. They've issued statements clarifying that speculation about artificial origin is not supported by their data analysis, and that the scientific consensus remains firmly in the natural comet camp. Several prominent astronomers have published rebuttals to the artificial hypothesis, systematically addressing each claimed anomaly and providing natural explanations. These papers are dense with mathematics, filled with error analysis and probability calculations, and they generally conclude that while 3I Atlas is interesting, it doesn't require invoking anything beyond known astrophysical processes to explain. The debate plays out not just in journals, but in media interviews, conference presentations, Twitter threads, and blog posts. It's science as a contact sport, with competing interpretations battling for mindshare in both the professional community and the public imagination. And like most scientific controversies, it's not purely about the evidence. It's also about philosophy, about what counts as good science, about the balance between skepticism and openness to new ideas, and about how to stay honest while staring into the unknown. One thing both sides agree on: we need better data, more observations, a longer baseline, higher resolution imaging, detailed spectroscopy across multiple wavelengths. If 3I Atlas were truly artificial, continued monitoring should reveal technosignatures that natural processes can't convincingly mimic. If it's natural, better data should clarify which natural processes explain the observations and gently put the exotic hypotheses to rest. The problem is that 3I Atlas is now receding from the sun, getting dimmer, harder to observe. The window for detailed study is closing like a slow shutter. Some astronomers are scrambling to secure more telescope time before the object fades beyond detection. Others argue resources would be better spent on targets with higher scientific priority. There's a real tension between the impulse to chase every anomaly and the practical reality of limited observational resources. What fascinates me about this debate isn't just the science, it's the sociology. The way careers and reputations get tangled in interpretations, the way institutional positions become entrenched, the way public communication feeds back into scientific discourse. Loeb's high media profile means his ideas travel far beyond the professional astronomy community, which some see as valuable science communication, and others see as irresponsible sensationalism. There's also a generational dimension. Older, more established astronomers tend toward conservative interpretations, having watched dozens of anomalies over their careers, eventually become mundane once better understood. Younger researchers, less invested in existing paradigms, might be more open to radical reinterpretation. But that's a generalization, and reality is messier than generational stereotypes. The critics aren't wrong to demand high standards of evidence before accepting extraordinary claims. That's how science prevents itself from sprinting after every wild idea that feels thrilling but lacks substance. The advocates aren't wrong to push against premature closure, to insist that unusual observations deserve unusual scrutiny. Both impulses are necessary for healthy science. What worries me is when the debate becomes more about personalities than evidence. When disagreement hardens into dismissiveness, when asking certain questions becomes professionally risky, science works best when it maintains a balance, rigorous in evaluating claims, but open to being surprised. That balance is hard to achieve, especially when media attention and public interest create pressures beyond the usual academic dynamics. So where does this leave us with a fascinating object? Incomplete data, competing interpretations, and passionate advocates on multiple sides, with institutional positions that may or may not be influenced by conservative bias, with a public trying to separate what's actually known from what's merely suggested, and with the reality that science is a human endeavor shaped by social dynamics as much as by pure logic. The truth about 3i Atlas will ultimately emerge from continued observation and analysis, not from who argues most forcefully or who racks up more media appearances. But until that truth emerges, the debate itself tells us something valuable about how science grapples with the genuinely unexpected. And maybe, just maybe, it reminds us that the universe doesn't care about our consensus positions or our comfort zones. It simply is what it is. Whether that fits our expectations or not. Part dies. Statistical and mathematical paradoxes. Numbers don't lie, but they can definitely mislead. And nowhere is this more apparent than in the statistical argument swirling around 3i Atlas. We need to talk about probability, about what makes something statistically significant versus statistically suspicious, because this is where the rubber meets the road in deciding whether the object is genuinely anomalous or just an expected outlier from natural variation. Let's start with the basics. When astronomers study populations of objects, comets, asteroids, stars, they build statistical models of what's normal. What's the typical range of compositions? How do rotation rates distribute? What geometries appear most frequently? These models let us identify outliers, objects that fall outside the expected range. And outliers are interesting because they might represent new physics, measurement errors, or simply the extreme tail of normal variation. 20i Atlas is an outlier. That much isn't disputed. The question is whether it's a surprising outlier or an expected one, and that depends entirely on how you calculate the probabilities, what assumptions you build into your models, and how you account for selection bias and multiple comparisons. Take the jet symmetry. For example, if you model jet formation as a random process, active areas emerging unpredictably on the surface and pointing in roughly random directions, what are the odds of getting 3 jets spaced at roughly equal intervals? You first have to specify what roughly equal means within 5 degrees, 10 degrees, 20 degrees. The tighter your requirement, the lower the probability, like narrowing a doorway in the dark. Some calculations suggest odds of 1 in several hundred for near-perfect triple symmetry. Others, using looser criteria, get odds closer to 1 in 50. Now, is 1 in 50 rare in everyday life? Yes, But in astronomy, where we've observed thousands of comets and could detect millions more, 1 in 50 means we should expect to see this occasionally. It's like being surprised that someone in your city won the lottery, even though statistically, someone somewhere wins every week. Rare for any single person, but not rare across the whole population. But here's where it gets complicated. The symmetric jets aren't the only unusual feature. There's also the composition anomaly, the carbon dioxide dominance that places 3I Atlas at the extreme tail of observed cometary chemistry. Let's say that's another 1 in 100 probability. And the unusual dust distribution, maybe 1 in 50. And the trajectory alignment, potentially 1 in several hundred, depending on how you define alignment. If these features are independent, you multiply the probabilities. 1 in 50 times, 1 in 100 times, 1 in 50 times, 1 in several hundred gives you odds in the millions. Suddenly, you're looking at a combination of features so unlikely that seeing it in one object strains credibility for the natural hypothesis. But that multiplication assumes independence, and that's a massive assumption. Many of these features might be causally related, different faces of the same underlying condition. For instance, unusual composition might drive unusual outgassing patterns, which create unusual dust distribution, which then affects how we perceive jet geometry. If that's the case, you can't multiply the probabilities, because they're not independent events. You're essentially counting the same anomaly multiple times. This is the multiple comparisons problem, and it's a notorious source of statistical deception. If you measure 100 different parameters on an object and find one that's unusual at the 1 in 100 level, that's exactly what random chance predicts. Finding something unusual when you're looking for anything unusual isn't impressive. What would be impressive is predicting in advance which specific parameter would be unusual and then finding it. Critics of the exotic hypothesis argue that this is exactly what's happening with 3I Atlas. Researchers measure every conceivable parameter, notice a few that look odd, and then retroactively claim the combination is too unlikely to be natural. It's like shooting an arrow at a barn and then painting a bullseye around wherever it landed. You can always find the target if you draw it after the shot. The counter-argument is that we're not just finding random, unusual parameters, we're finding features that cluster around a coherent alternative hypothesis, artificial origin, or at least highly unusual formation conditions. The anomalies aren't scattered randomly across all possible measurements. They're concentrated in areas that would matter if this were an engineered object. That pattern within the anomalies is itself statistically meaningful. But even that argument has problems. Human brains are pattern-matching machines. We see constellations in random star positions, faces in clouds, conspiracies in coincidence. The fact that we can construct a narrative connecting the anomalies doesn't prove the narrative is correct. It might only prove we're good at storytelling, especially when the story feels like it could be true. Let's talk about trajectory alignment, because this is where the mathematical arguments get genuinely heated. Some analyses claim that 3I Atlas's rotation axis is aligned with its velocity vector, or with the sun's direction, to a degree that's statistically improbable. If true, that would be bizarre, because there's no known mechanism that would create such alignment in a natural object. Angular momentum and velocity are independent quantities. Why would they line up? The devil is in how you measure alignment. Do you use the instantaneous axis, or an average over time? Do you account for precession and wobble? What coordinate system do you use? Different choices can yield different answers, and critics claim that by trying enough definitions, you can always find one that shows apparent alignment by chance. It's data dredging, finding significance through selective analysis rather than a genuine effect. Supporters of the alignment claim counter that the effect persists across multiple independent analyses using different methods. That wouldn't be expected if it were just statistical noise or selective reporting. Multiple teams seeing similar patterns strengthens the case that something real is there, even if we're not sure what it means. The composition statistics are perhaps the most solid, because we have better data and clearer models. The carbon dioxide to water ratio in 3I Atlas is genuinely extreme compared to the population of observed solar system comets. You can calculate precise odds based on the distribution of known objects, and those odds are legitimately small, not 1 in 50, but more like 1 in several thousand. However, and this is crucial, we're not comparing to a random solar system comet. We're comparing to an interstellar comet. And our sample size, there is exactly 2 Oumuamua and 3 I Atlas. Making statistical claims about a population when you have 2 samples is, to put it mildly, problematic. Maybe all interstellar comets have weird chemistry. Maybe the 2 we've detected are both outliers from their home systems, which is why they got ejected in the first place. We simply don't know. There's also the question of what probability threshold should trigger a paradigm shift. Science doesn't have a single answer here. The particle physics standard for claiming a discovery is 5 sigma odds of less than 1 in 3, 5 million of being wrong. Medical research uses lower thresholds. Astronomy is somewhere in between. Context dependent. For a routine measurement, 2 or 3 sigma might suffice. For claiming alien technology, you'd want much higher confidence. Some researchers have tried to formalize this using Bayesian analysis, which explicitly incorporates prior beliefs into probability calculations. If your prior belief is that artificial objects are extremely rare, then even moderately anomalous data won't shift you much toward the artificial hypothesis, because the prior is so strong. If you start with a more agnostic prior, the same data might look more compelling. The math is correct in both cases. The difference is in the starting assumptions. What frustrates me about all these statistical arguments is how easily they can be wielded to support whatever conclusion you already favor. Conservative researchers emphasize multiple comparisons, selection bias, and the flexibility of natural processes. Advocates for exotic hypotheses emphasize cumulative improbability and the clustering of anomalies. Both can construct mathematically valid arguments. Because the underlying uncertainties are large enough to accommodate multiple interpretations, the honest answer is that our statistical tools are better at detecting clear signals than at evaluating messy, multidimensional anomalies where features might or might not be independent, where sample sizes are tiny, and where prior beliefs dramatically affect conclusions. We're operating at the limits of what statistics can definitively tell us, and pretending otherwise is misleading. What we can say is this 3I Atlas shows combinations of features that are unusual, potentially very unusual, but quantifying exactly how unusual requires assumptions that reasonable people can disagree about. The object is statistically interesting, worth detailed study, but whether it crosses the threshold from interesting to paradigm depends on factors beyond pure mathematics. And sometimes the most important number is the one we don't have yet, the data point still missing. Part owns. Violent planetary formation seen live. Let's step back from 3I Atlas for a moment and talk about other ways the universe has recently reminded us we don't know nearly as much as we think we do. Because while we've been obsessing over one weird object in our solar system, telescopes have been capturing other cosmic events that are equally mind-bending, and they provide context for why anomalies shouldn't shock us as much as they do. In 2024 and 2025, the Hubble Space Telescope observed something astronomers had theorized about, but never directly witnessed: massive asteroid collisions in other stellar systems caught in the act. We're not talking about gentle bumps between pebbles. We're talking about catastrophic impacts between kilometer-sized bodies, events energetic enough to vaporize mountains and spray debris across millions of kilometers of space. The kind of violence that shaped our own solar system billions of years ago, now visible in real time around distant stars. These observations are revolutionary because they're giving us a direct window into planetary formation processes we've only inferred from our own solar system's structure and meteorite compositions. The early solar system was a chaotic shooting gallery, with protoplanets and planetesimals constantly smashing into each other, accreting mass, fragmenting, reaccreting. It was geological violence on a cosmic scale, and it's the crucible from which Earth and the other planets emerged. But that happened 4 billion years ago. We missed the show. All we have are the frozen remnants, the asteroids and comets that survived, the chemical signatures in meteorites that whisper of ancient impacts. It's like trying to reconstruct a war from the bullet casings left behind. You can infer what happened, but you're not watching it unfold. Now, with sufficiently powerful telescopes pointed at young stellar systems, we're finally seeing planetary formation in action. and it's even more chaotic and violent than models predicted. The dust clouds that erupt from these impacts are enormous, detectable across light years. The debris disks they create can persist for thousands of years. The chemical signatures show vaporized rock flash, heated to thousands of degrees, rapidly cooling into exotic mineral phases that don't exist naturally on Earth. What does this have to do with 3I, Atlas, everything and nothing? It's a reminder that our solar system, as familiar as it feels, isn't necessarily representative of cosmic norms. We formed in one particular molecular cloud, with one particular chemical mix, under one particular set of conditions. Other stellar systems form differently, experience different collisional histories, and produce different populations of leftover debris. When an object from one of those systems visits ours like 3I Atlas, there's no reason to expect it to look like the comets and asteroids we're used to. It might have a completely different chemistry because it formed in a different chemical environment. It might have unusual structure because it's a collision fragment rather than a pristine, primordial body. It might exhibit behaviors we haven't seen before because it experienced formation conditions we don't have locally. The planetary formation observations also highlight how much of cosmic evolution is driven by stochastic, chaotic processes. Yes, there are patterns and regularities. Planets tend to form in disks. Large bodies tend to migrate inward or outward based on angular momentum transfer, but within those broad trends, there's enormous variation. Every stellar system is unique in its details, shaped by the timing and magnitude of collisions, the distribution of materials, the gravitational perturbations from nearby stars. This matters for how we interpret anomalies. If cosmic processes were deterministic and uniform, an object that differs significantly from our local population would be genuinely shocking. But processes aren't uniform. They're messy, path-dependent, influenced by random fluctuations that get amplified through chaotic dynamics. Outliers are expected. Weird is normal when you're sampling from a population shaped by chaos. Another recent discovery worth mentioning is the detection of unusual dust distributions around certain stars, structures that don't fit standard models of protoplanetary disks. Some show gaps and rings that might indicate forming planets, but the patterns are more complex than simple gravitational perturbation predicts. Others show asymmetries, clumps, arcs, spirals that hint at gravitational instabilities or outside perturbations we still don't fully understand. These images are forcing theorists to reopen old notebooks on disk evolution and planet formation. Maybe magnetic fields matter more than we assumed. Maybe turbulence is the real sculptor. Maybe there are processes we haven't even named yet. The point is, models that felt robust when tested mostly against our solar system's architecture are showing hairline cracks when confronted with the sheer diversity of real systems. And if we're wrong about planetary formation, if it's more variable and intricate than we realized, then predictions about what leftover debris should look like become less reliable. The boundaries of normal start to blur. An object that seems anomalous by solar system standards might be perfectly ordinary by galactic standards. We just haven't built our models wide enough yet to recognize it. The violence of early stellar systems also has implications for composition. High-energy impacts don't just shuffle rock and ice around. They drive chemistry. They create temperatures and pressures that forge new minerals, crack molecules into fragments that recombine in novel ways, and mix materials that would normally remain separate like layers in a quiet cake. A fragment ejected from such an impact could carry a composition shaped by those extremes, potentially explaining unusual chemistry without invoking exotic origins or impossible stories. There's something humbling about watching cosmic violence unfold in other stellar systems. It reminds us that our serene, stable solar system is a middle-aged remnant of a far more turbulent youth. The calm we observe is temporary on cosmic timescales. Billions of years from now, when the sun swells into a red giant, our own system may experience another round of chaos as orbits shift and bodies collide or get flung outward into the dark. So when we encounter an interstellar visitor like 3I Atlas and find it doesn't match our expectations, maybe the right first response isn't to assume it's artificial or even necessarily exotic. Maybe it's to recognize our expectations are calibrated to one data point, one stellar system, one formation history, one familiar neighborhood. The galaxy is vast, diverse, and quietly inventive in ways we're only beginning to appreciate. That said, unusual doesn't mean we ignore it. Outliers are where new understanding often begins. They're the discrepant observations that force revisions, the stubborn details that reveal gaps in our knowledge. 3i Atlas is valuable precisely because it challenges our models, whether it ultimately fits within expanded natural categories or represents something genuinely unprecedented. The broader lesson from recent astronomical discoveries is that the universe is stranger and more variable than our theories often account for. Black holes are more common than we once thought. Exoplanets come in architectures we didn't predict. Stellar evolution keeps slipping surprises into the margins. Why should small bodies, comets, and asteroids be any different? Why should we expect cosmic debris to obey our narrow, local expectations? We shouldn't. And recognizing that doesn't diminish the intrigue of 3i Atlas. It contextualizes it. This object is a messenger from another corner of the galaxy, carrying information about conditions and processes we don't experience locally. Whether that information updates our understanding of natural cosmic diversity or points towards something more radical remains to be determined. But either way, it's teaching us something, and that, ultimately, is what science is being surprised. Investigating the surprise, and letting reality update our models instead of forcing observations to fit our comfort. The universe is under no obligation to conform to our theories. It simply does what it does, indifferent to our certainty or confusion. And right now, what it's doing includes sending us an object that makes us question assumptions we didn't even know we were making. Part 2's 2025's biggest scientific breakthroughs. Before we dive back into the deep end of speculation about 3i Atlas, let's pause and appreciate what an absolutely bonkers year 2025 has been for discovery across multiple fields. Because one mystery makes more sense in context, and that context is a universe that keeps revealing itself to be more complex, more dynamic, and more surprising than we imagined. Let's start with dark energy, that mysterious driver behind the accelerating expansion of the universe. For decades, the standard cosmological model treated dark energy as constant, unchanging across space and time. But new measurements from multiple independent sources, including observations from the James Webb Space Telescope and major ground-based surveys, have suggested that dark energy might not be constant after all. It might be varying over cosmic time, which would fundamentally shift our understanding of the universe's fate. If dark energy is truly variable, it opens possibilities ranging from the mundane to the existential. Maybe it's not a property of space itself, but a dynamic field that evolves. Maybe expansion won't accelerate forever. It might slow down, speed up more dramatically, or even reverse into a big crunch billions of years from now. The implications cascade through cosmology, reshaping everything from galaxy formation models to the ultimate destiny of matter itself. Then there are the black hole observations that have been absolutely wild. The Event Horizon Telescope collaboration, the team that gave us the first direct image of a black hole's shadow, has been releasing new data showing unprecedented detail in magnetic fields and plasma flows around these cosmic monsters. They've captured what appears to be material plunging toward the event horizon in near real time, reinforcing predictions from general relativity with a kind of eerie visual clarity. But it's not just supermassive black holes grabbing headlines. Observations of stellar mass black holes, the kind born from collapsed stars, have revealed unexpected behaviors. Some accrete matter in ways that don't match standard disk models. Others produce jets with properties that challenge our understanding of magnetic field amplification and particle acceleration. It's like we've been studying black holes for 50 years and only recently realized we were mostly seeing the simplest cases. The full diversity is richer, stranger, and harder to summarize in a neat diagram. Astrobiology has had its own exciting year. Though with the usual caveats about not outrunning the data, new observations of Mars by the Perseverance rover have turned up organic molecules in sedimentary rocks with structural complexity that's difficult to explain through purely abiotic processes. Not proof of life, not even close, but suggestive enough that the scientific community is taking it seriously. The possibility that Mars once hosted microbial life is shifting from maybe to worth serious. Sustained investigation. Exoplanet science continues its relentless march toward finding an Earth too. Ling. The James Webb Space Telescope has characterized atmospheres of several rocky planets in habitable zones around their stars, and while none show clear biosignatures yet, the data quality is improving to the point where detecting oxygen, methane, and other potential indicators of life is becoming technically feasible. We're not there yet, but we're close enough to start arguing about what would actually count as convincing evidence and what would still be ambiguity in a prettier suit. Gravitational wave astronomy has matured from infancy to adolescence. The LIGO, Virgo, and CAGRA detectors are now routinely detecting mergers of black holes and neutron stars, sometimes multiple events per week. But more exciting are hints of signals that don't fit standard merger templates. Could be instrumental artifacts. Could be new kinds of sources. Could be gravitational waves from the very early universe ripples in space-time that have been traveling for over 13 billion years. The jury is still out, but the possibilities are quietly tantalizing. Particle physics has been relatively quiet on the new particle front. Much to physicists' frustration, the Large Hadron Collider hasn't found the supersymmetric particles or extra dimensions many theories predicted. But absence of evidence is itself informative, forcing theorists to revise or abandon models that once looked elegant on paper. Sometimes science moves forward by ruling things out, narrowing the space of possibilities until the truth has fewer hiding places. Neutrino physics, though, has delivered surprises. New measurements of neutrino oscillations, the way these ghostly particles change identity as they travel, have revealed discrepancies with the standard model that might point toward new physics. Maybe there are additional kinds of neutrinos. Maybe their masses are distributed differently than we thought. Maybe matter and antimatter behave differently in the neutrino sector, which could help explain why the universe has more matter than antimatter. Closer to home, climate science has been refining models of Earth's feedback systems with sobering precision. New satellite data and improved computational models are revealing how ice sheet dynamics, ocean circulation, and atmospheric chemistry interact in ways more intricate than previously understood. The broad picture of anthropogenic warming hasn't changed, but the regional details and timescales are becoming clearer and, in many cases, more urgent than earlier projections suggested. Materials science has seen fresh breakthroughs in the pursuit of room temperature superconductors, though. As always, replication is everything. Several groups have reported materials that show zero electrical resistance at relatively high temperatures and near normal pressures, which would be revolutionary for energy transmission and countless other applications. But previous claims of room temperature superconductivity have failed to replicate. So the community is being appropriately cautious while intensely interested, watching the data like a candle flame that might either steady or flicker out. Artificial intelligence continues to evolve at a pace that makes year-to-year comparisons almost comical. Models are now tackling protein folding, climate prediction, drug discovery, and theorem proving with capabilities that seemed impossible just a few years ago. The philosophical and practical implications of increasingly capable AI systems are shifting from academic debate to urgent societal concern. As these tools become powerful enough to reshape industries and potentially pose risks if misaligned with human values. And woven through all these developments is the ever-present theme of instruments getting better, data getting richer, and reality surprising us anyway. The Vera C. Rubin Observatory is about to come online, promising to revolutionize our understanding of transient astronomical phenomena and small bodies in our solar system. Next-generation telescopes are in development that will make even James Webb look primitive by comparison. Computing power continues to grow, enabling simulations of unprecedented scale and complexity, digital universes humming beside the real one. What does all this have to do with 3i Atlas? Its context. It's a reminder that science isn't static, that our understanding is constantly being updated, that models we thought robust are revealed to have gaps or edge cases. When we encounter an astronomical anomaly, we're not evaluating it against settled, complete knowledge. We're evaluating it against provisional frameworks we already know have limitations and will be revised as more data arrives. 2025 has been a year of surprises across multiple domains of science. Dark energy might not be constant, Black holes are more complex than we modeled. Mars might have hosted life. Neutrinos may be hiding secrets. Each of these developments has required scientists to expand or revise theories to admit that previous models were incomplete. So when we look at 3I Atlas and find it doesn't quite fit our Comet models, the appropriate response isn't to defend the models at all costs. It's to investigate whether the models need updating. Maybe this object will teach us something about interstellar chemistry we didn't know. Maybe it'll reveal formation processes we hadn't considered. Maybe it'll expand our taxonomy of small bodies to include new categories. Or maybe, just maybe, it'll force us to confront possibilities we've been too timid to seriously entertain. But we won't know unless we keep looking. Keep measuring. Keep testing hypotheses against evidence instead of dismissing anomalies because they're inconvenient. Science in 2025 is a reminder that the universe is under no obligation to be simple, predictable, or consistent with our current theories. It is what it is, and our job is to understand it, not to insist it conform to our preferences. And right now, among all the cosmic mysteries under the microscope, 3I Atlas stands out as one that might rewrite what we thought we knew about objects traveling between the stars. The question is whether we're ready for what that rewrite might say. Part Trays. Alien tech theories resurfacing the 8 hypotheses. All right, we've been dancing around this topic for the entire script. Dropping hints. Acknowledging possibilities. Being appropriately cautious and scientific. But let's be honest about why 3I Atlas has captured the public imagination, and why it's generating headlines that make professional astronomers cringe. It's because of the question everyone's thinking, but most scientists won't address directly: could this thing be artificial? Avi has laid out 8 specific observations about 3I Atlas that he argues are consistent with, though not proof of artificial origin or technological modification. Let's walk through them, not to endorse them, but to understand the argument and evaluate it fairly. Because even if the probability is low, even if it's vanishingly unlikely, the question deserves serious consideration rather than reflexive dismissal. Hypothesis 1, the trajectory alignment. Loeb and others have noted that certain aspects of 3I Atlas's path through the solar system show what they interpret as non-random alignment with specific celestial reference points. If you were navigating through interstellar space, you might orient your trajectory relative to the galactic plane or nearby bright stars. A natural object would have no reason to do this. Its path is determined purely by the gravitational slingshot from its home system and random perturbations along the way. The counterargument is that apparent alignment is subjective, dependent on how you define the reference frame, and that, with enough possible alignments to check, you'll always find one that looks meaningful by chance. Hypothesis 2, the unusual tail geometry. We've discussed the anti-tail features and the possibility of sunward-pointing material. Loeb argues that the specific configuration observed is difficult to explain through standard comet tail physics, which are well understood and rarely produce persistent sunward features of the type reported. If you wanted to use controlled outgassing for propulsion, you might direct exhaust in specific directions that could create tail geometries inconsistent with passive sculpting by solar wind and radiation pressure. The counterargument is that anti-tails are rare but documented. Optical effects can create illusions of sunward material, and claiming this is fundamentally different requires more rigorous analysis than has been presented. Hypothesis 3, the symmetric jet structure. We've beaten this one to death, but it's central to the argument. Triple jets, at equal intervals, if real, suggest a level of organization that randomized distribution and chaotic surface topography wouldn't naturally produce. Engineering thruster placement for stability would create exactly this kind of symmetry. The counterargument remains that symmetric features can arise naturally under specific conditions, that the symmetry isn't as perfect as claimed, and that confirmation bias may be making people see regularity and noise. Hypothesis 4, the carbon dioxide dominance and unusual chemistry. An object designed for controlled sublimation might be engineered with specific volatile compositions to optimize thrust efficiency or other performance characteristics. Carbon dioxide has different sublimation properties than water and might be preferred for certain engineering applications. The counterargument is that interstellar objects can have different chemistry than solar system natives without invoking engineering, that cosmic ray processing can explain exotic compositions, and that our sample size of interstellar comets is too small to define normal. Hypothesis 5. The lack of a significant dust tail. Some observations suggest 3I Atlas produces less dust than expected for its level of gas production. If you're using ice sublimation for propulsion, you'd want to minimize dust because it represents wasted mass that doesn't contribute to thrust. You might design a system with relatively pure volatiles, minimizing rocky contaminants. The counterargument is that dust production varies widely among natural comets based on composition and structure, that observing conditions affect dust detection, and that the absence of an obvious dust tail doesn't imply the absence of natural processes. Hypothesis 6. The rotational stability. Some analyses suggest the object's rotation is unusually stable or aligned compared to typical tumbling small bodies. A designed object might maintain intentional spin for stability or communication purposes through thruster adjustments or internal mass distribution. Natural objects tend to tumble chaotically unless they're large enough for self-gravity to enforce stability. The counterargument is that rotation observations are difficult and interpretive, and that many natural small bodies do maintain relatively stable rotation, especially if past collisions shape them into roughly symmetric forms. Hypothesis 7. The size and mass estimates. Based on various observations, 3I Atlas appears to sit in a size range that's energetically plausible for interstellar transport, with advanced propulsion technology neither so small as to be insignificant nor so large as to be impractical. If you were building an interstellar probe and wanted to use a comet-like object as camouflage or as actual fuel, you might choose dimensions in this range. The counterargument is that natural comets span an enormous size range, that we're seeing 3I Atlas because it's in the detectable size range, and that claiming a size is suspicious because it's plausible for technology is unfalsifiable reasoning. Hypothesis 8. The velocity and trajectory that brought it into our solar system. Some argue that the specific approach vector and speed are suspiciously well suited for a close pass through the inner solar system, as if the trajectory were intentionally designed for a flyby mission. A random ejection from another stellar system would be less likely to have such convenient orbital parameters. The counterargument is that we only detect interstellar objects that pass close enough and bright enough to be seen, creating selection bias, and that calling a trajectory suspicious because it brought the object near us is circular reasoning, when we only notice objects that come near us. Now, having laid out all 8 hypotheses, let me be extremely clear: none of these, individually or collectively, constitute proof or even strong evidence of artificial origin. What they constitute is a set of observations that some researchers interpret as anomalous enough to warrant serious investigation of exotic possibilities, while other researchers interpret them as within the bounds of natural variation, unusual, perhaps, but not inexplicable. The fundamental problem with the artificial hypothesis is the lack of positive evidence. We don't see radio transmissions. We don't see optical flashes. We don't detect refined metals or industrial pollutants. And we don't observe trajectory corrections beyond what outgassing can explain. All we have is an imperfect fit with natural models. And an imperfect fit isn't the same as evidence of artificiality. It's a sign that our models might be incomplete. But, and this matters, absence of techno-signatures doesn't definitively rule out artificial origin either. A sufficiently advanced and patient civilization might design objects that don't broadcast their nature, drifting quietly like dark buoys between stars. Maybe they use natural materials precisely to avoid detection. Maybe they've been traveling for millions of years and their tech is degraded or dormant. Maybe our methods are looking for the wrong signatures. Arguing from absence is tricky in both directions. The comparison to Oumuamua is inevitable. That object generated similar speculation when it showed non-gravitational acceleration that some interpreted as artificial propulsion. Subsequent analysis suggested outgassing of hydrogen too diffuse to detect directly could explain the acceleration naturally. The exotic hypothesis wasn't needed once the data was properly analyzed. Many astronomers see 3I Atlas as Oumuamua 2, Ling, another case where initial anomalies will resolve through better understanding of natural processes, but there's a key difference. With Oumuamua, we had very limited data because it was already leaving the solar system when detected. With 3I Atlas, We caught it earlier, observed it more thoroughly, and still have anomalies that resist easy explanation. That doesn't make the artificial hypothesis more likely, necessarily, but it does mean natural explanations have had more time to mature and still haven't achieved consensus. What bothers me about the entire alien tech discussion is how it polarizes the conversation. Advocates get dismissed as cranks. Skeptics get accused of closed-mindedness. The actual science, the careful evaluation of competing hypotheses against evidence, gets lost in the noise of tribal signaling about whether you're a believer or a debunker. The truth is, we should be skeptical of artificial origin because it requires extraordinary assumptions about alien civilizations, their technologies, and their motivations. But we should also be open to the possibility, because ruling it out without investigation would be a failure of scientific curiosity. The balance point is taking the hypothesis seriously enough to test it rigorously, while demanding high standards of evidence before accepting it. And right now, we don't have that evidence. We have anomalies, questions, and incomplete data. What we need is continued observation, better measurements, and the intellectual humility to admit when we don't know, rather than forcing premature conclusions in either direction. The alien tech theories will persist as long as the anomalies do. They'll be dismissed by most scientists, entertained by a minority, and obsessed over by the public. And eventually, with enough data, we'll have an answer. Maybe that answer will be mundane. Maybe it'll be paradigm shifting. But the asking of the question, uncomfortable as it makes many people, is itself valuable. Because if we aren't willing to investigate the most interesting possibilities, even the unlikely ones, are we really doing science or just confirming what we already believe? Part 14. Unexplained chemical signatures in space. Let's broaden our perspective beyond 3I Atlas and talk about how the chemical story of this object fits into a larger pattern of cosmic chemistry that keeps defying expectations. Because unusual molecules aren't limited to weird interstellar visitors, the universe is a vast chemistry lab conducting experiments we're only beginning to recognize. Astronomers have been detecting complex organic molecules in space for decades, and each new discovery pushes the boundaries of what we thought possible in the harsh radiation environment of interstellar clouds and circumstellar regions. We've found amino acids in meteorites, the building blocks of proteins. We've detected polycyclic aromatic hydrocarbons, complex carbon rings forming in stellar outflows. We've identified sugars, alcohols, and even molecules with structures that hint at proto-biological significance. The discovery of methanol and hydrogen cyanide in 3I Atlas places it in this broader context of cosmic chemistry. Methanol is a relatively simple alcohol, common in molecular clouds, where it forms on dust grain surfaces through reactions between carbon monoxide and hydrogen. Finding it in a comet isn't surprising. What's surprising is the abundance relative to water. High methanol ratios suggest formation in very cold, dark environments where water ice doesn't dominate as completely as it does in warmer regions. Hydrogen cyanide is even more interesting from an astrobiological perspective. It's a key precursor to adenine, one of the nuclear bases in DNA and RNA. Laboratory experiments have shown that hydrogen cyanide can polymerize into complex organic molecules relevant to life's origin. Finding it in an interstellar object supports the hypothesis that life's chemical ingredients are common in the universe, delivered to planetary surfaces by comet and asteroid impacts. But beyond these, expected if exciting molecules, there are the weird ones. The reported nickel tetracarbonyl detection, if confirmed, would be genuinely bizarre. We've detected metal-bearing molecules in space before aluminum oxide in stellar atmospheres, iron and magnesium compounds in planetary nebulae, but they're typically simple oxides or sulfides. Complex organometallic compounds like nickel tetracarbonyl are rare and require specific formation conditions that aren't obviously present in most astronomical environments. Laboratory astrochemistry has been trying to understand how such molecules could form. One pathway involves metal atoms ejected from dust grains by cosmic rays or ultraviolet radiation, reacting with carbon monoxide in the gas phase. Under the right temperature and pressure conditions, these atoms can bind multiple carbon monoxide molecules, creating the carbonyl structure. It's chemically plausible, but it demands a delicate balance of conditions, and we're not sure those conditions persist in interstellar space long enough to build significant concentrations. Another possibility is surface chemistry on dust grains. These microscopic particles provide catalytic surfaces where reactions that would be prohibitively slow in the gas phase can proceed efficiently. Molecules absorb onto the grain, drift across its surface until they meet reaction partners, form bonds, and then desorb back into the gas. Complex chemistry, including the formation of organic molecules and, potentially, certain metal compounds, can unfold through this quiet mechanism. The cosmic ray processing we keep mentioning is also relevant to chemistry, far beyond just 3I Atlas. High-energy particles don't merely snap chemical bonds. They also inject energy into endothermic reactions that wouldn't proceed under normal, frigid interstellar conditions. They can drive the synthesis of complex molecules, alter isotopic ratios in ways we can detect, and create chemical environments unlike anything we can easily reproduce in terrestrial laboratories. Recent observations of molecular clouds, the vast nurseries of gas and dust where stars are born, have revealed chemical complexity that challenges our models of interstellar chemistry. We're finding molecules with 10, 15, even 20 atoms, structures that, on paper, should be destroyed by radiation faster than they're created. Yet they persist, somehow protected, or continuously regenerated. Understanding how requires rethinking assumptions about cloud structure, radiation field properties, and the tangled web of chemical reaction networks. Exoplanet atmospheres are another frontier of chemical discovery. James Webb Space Telescope observations have detected molecules in hot Jupiter atmospheres that weren't predicted by equilibrium chemistry models, sulfur dioxide, silicates, even possible biosignature gases in concentrations that don't match what we'd expect from purely photochemical or thermochemical processes. Either the models are wrong, which is entirely possible, or these atmospheres are more dynamically active and chemically complex than we anticipated. The implications of cosmic chemistry extend directly into questions about life's origin and ubiquity. If complex organic molecules are common in interstellar space, and if comets and asteroids deliver them to planetary surfaces during heavy bombardment phases, then the chemical precursors for life might be available on most rocky planets in habitable zones. This doesn't mean life is common, only that the raw materials may be, which shifts the question from where did the chemicals come from to what conditions allow those chemicals to organize into living systems. 3I Atlas, in this broader chemical context, is a single data point in a vast population of objects we're just beginning to characterize. Every comet, every asteroid, every interstellar visitor carries a chemical story about where it formed, what it endured, and what processes shaped its composition across deep time. We've studied solar system comets extensively, but they all share a broadly common formation environment. Interstellar objects sample different stellar systems, different birthplaces, potentially wildly different chemical inventories. As we detect more interstellar visitors in the coming years and decades, we'll build a statistical understanding of what's normal for objects from other stars. Maybe 3I Atlas will turn out to be typical, and it's our solar system that's the outlier. Maybe it's genuinely unusual, even by galactic standards. We won't know until we have a larger sample. The chemistry angle also connects to the artificial hypothesis in ways that are uncomfortable for mainstream scientists. If you were designing an object for interstellar travel using sublimation propulsion, you'd care about the chemistry. You'd want volatiles that sublime at useful temperatures, that provide strong thrust-to-mass ratios, that don't clog vents with dust. You might engineer chemical compositions that don't occur naturally, but are optimized for mission requirements. And this doesn't mean unusual chemistry implies artificiality. It means chemistry can't definitively rule it in or rule it out. Natural processes can be astonishingly creative, with molecular synthesis given enough time and enough diversity of conditions. But engineered chemistry would also look like molecules, and might not carry obvious fingerprints, separating it from exotic natural chemistry. What we need, and what's slowly coming, is comprehensive spectroscopic databases of interstellar and circumstellar environments, laboratory measurements of reaction rates under space-like conditions, and better theoretical models of astrochemistry. As these improve, we'll be able to say with more confidence whether observed chemical signatures require exotic natural explanations or whether they point towards something more radical. The universe is a chemist with billions of years of experience and a laboratory the size of galaxies. It's created everything from the simplest hydrogen molecules to the staggeringly complex chemistry of living cells. Finding weird molecules in space shouldn't shock us. What should shock us is ever believing we've catalogued all the possibilities. 3. Atlas's chemistry is weird. But weird chemistry is, in a sense, exactly what you'd expect from a universe with unlimited time and countless experimental conditions to explore molecular configurations. Whether this particular combination of weird requires updating our natural chemistry models or points towards something beyond natural chemistry remains an open question. And like most good questions in science, the answer is probably we need more data. Part Keynes. Closing. Look, the frontier of cosmic mystery. So here we are. At the end of this journey through one of the most fascinating astronomical puzzles of our time, we've looked at the hard data from Hubble and James Webb. We've examined the anomalies that don't quite fit standard comet models. We've listened to conservative voices urging caution, and provocative voices urging us to expand our thinking. We've placed 3I Atlas in the broader context of planetary formation, chemical discoveries, and the recurring pattern of cosmic surprises. And after all that, what can we actually conclude? The honest answer is not as much as we'd like, but more than we started with. 3I Atlas is definitely unusual. The carbon dioxide dominance is real, confirmed by multiple instruments using different techniques. The jet structures, while subject to interpretation, show features that at minimum deserve further study. The dust distribution, the brightness variations, the chemical signatures each contains information we're still learning to decode. What we can say definitively is that this object is pushing the boundaries of our understanding of comets, or perhaps demonstrating that our category of comet is too narrow, too shaped by parochial solar system experience. Whether it's pushing us toward recognizing new natural categories or toward considering more exotic possibilities depends heavily on your prior beliefs, your tolerance for uncertainty, and your interpretation of statistical significance. The scientific process will eventually sort this out. More observations will accumulate, either explaining the anomalies through refined natural models or deepening the mystery to the point where alternative hypotheses must be seriously entertained. The James Webb Space Telescope is continuing to monitor 3I Atlas as it recedes from the Sun, gathering long-term data on how its activity changes with solar distance. Ground-based telescopes are tracking its trajectory, looking for any deviations that can't be explained by outgassing. Future missions might give us even better tools. The Rubin Observatory, when it comes fully online, will dramatically increase our detection rate of interstellar objects, potentially finding dozens or hundreds over the next decade. Each one will provide another data point, helping us understand whether 3I Atlas is an outlier or representative of a broader population. If we find many similar objects, the exotic hypothesis becomes less appealing. If 3I Atlas remains unique even among a larger sample, that's when things get truly interesting. There are also technological advances on the horizon that could directly interrogate objects like this. Proposals exist for fast flyby missions that could reach interstellar visitors quickly enough to make close observations before they leave the solar system. Imagine a spacecraft passing within hundreds of kilometers of 3I Atlas, taking high-resolution images, direct spectroscopy, maybe even particle sampling. That kind of data would resolve many current debates decisively. Artificial intelligence and machine learning are being applied to astronomical data analysis in ways that might reveal patterns humans miss. Algorithms trained on thousands of comets might identify subtle signatures in 3I Atlas that distinguish it from natural objects, or confirm it as an extreme but natural example. These tools are still developing, but they represent a new approach to interpreting the massive datasets modern telescopes generate. But beyond the specific case of this one object, there's a larger question about how we approach cosmic anomalies. Science requires skepticism, the refusal to accept claims without evidence. But it also requires openness, the willingness to update models when observations don't fit. Balancing these impulses is hard, especially when the consequences of being wrong in either direction are significant. If we're too skeptical, too committed to defending existing paradigms, we might miss genuine discoveries. History is full of rejected ideas that later proved correct because evidence was dismissed prematurely. But if we're too credulous, too quick to embrace exotic explanations, we waste resources chasing phantoms, and we undermine public trust in science by hyping claims that don't pan out. 3. Atlas sits right at this uncomfortable boundary, conservative enough to be explainable, exotic enough to be intriguing, the perfect test case for how modern astronomy handles ambiguity and uncertainty. And honestly, I find our collective response encouraging. Yes, there's debate. Yes, there's disagreement. But there's also serious investigation, rigorous analysis, and a willingness among most parties to let evidence lead rather than ideology. What excites me most about this whole affair isn't whether 3I Atlas is natural or artificial, though I'm curious about that too. What excites me is the reminder that we're still in the early stages of understanding the cosmos. We've barely begun cataloguing the diversity of objects in our own solar system, let alone the broader galaxy. Every new instrument, every new discovery, reveals how much we don't know. The universe is under no obligation to be simple, predictable, or aligned with human intuition. It simply is vastly complex and endlessly surprising. Our job, as scientists and as curious humans, is to observe carefully, think rigorously, and remain humble about the limits of current knowledge while staying confident in the power of systematic investigation to eventually approach the truth. 3I Atlas will continue its journey, receding into the darkness of interstellar space, eventually becoming too faint to observe. But the questions it's raised will persist. The data it's provided will be analyzed for years. And whether it's remembered as an interesting but natural comet, or as the object that forced us to confront uncomfortable possibilities, it has already served a valuable purpose by making us think harder about what we think we know. So keep watching the skies, keep questioning assumptions, keep demanding evidence while staying open to surprise. Because somewhere out there, between the stars, other objects are traveling through the cosmic night. Some will be mundane, some will be fascinating, and maybe, just maybe, some will be genuinely unprecedented. The frontier of cosmic mystery isn't somewhere distant and unreachable. It's right here, in objects like 3I Atlas that force us to confront the gaps in our understanding. It's in the space between what we've observed and what we can explain, in the tension between natural and artificial, known and unknown. And the beautiful thing about frontiers is that they keep moving. Every question answered reveals new questions waiting behind it. Every mystery solved uncovers deeper mysteries underneath. The cosmos is a puzzle with infinite pieces, and we've barely started working on the edges. 3I Atlas is just one piece, but it's a fascinating one, irregular in shape, hard to place, potentially connecting to parts of the puzzle we haven't even found yet. Whether it fits into the picture we're building or forces us to reconsider the entire image remains to be seen. But I, for one, can't wait to find out. And I hope you're just as curious, because the universe is vast, strange, and endlessly creative. And we're lucky enough to live in an age where we have the tools to investigate it, the freedom to question it, and the capacity to be quietly amazed by it. So here's to 3I Atlas, whatever it is. Here's to the questions it's raised and the investigations it's inspired. Here's to the scientists working long hours to understand it, the skeptics keeping us honest, and the speculators pushing boundaries. And here's to the next mystery already out there somewhere, waiting to capture our attention and challenge our understanding. The cosmos isn't done surprising us. It's only just getting started. And that more than any single discovery is the most exciting truth of all. Keep looking up, keep asking questions, and never assume we've seen everything the universe has to offer, because we haven't, not even close.